Everyone, I'm going to get us started. So if you can grab a coffee, grab a seat. Good morning and welcome to the first annual Energize Symposium. I am Malika Jeffrey-Zell, Professor of Chemistry, Senior Associate Dean for the Graduate School in Arts and Sciences, and the Director of the program. I also want to give a shout out to Emily Ryan, my co-director, my team, which includes David Coker, Brian Coolis, and James Chapman. I think James is doing drop-off. James is here. Brian's missing, drop-off. Who also helped support this effort, as well as Jesse, our program coordinator, Siri, who is a staff member here, for all of their support. But mostly I want to thank the students who came up with this vision and did the legwork to make this symposium a success. A little backstory on the NRT program. These are NSF research training programs, and the idea is to come up with a topic and to bring students together across disciplines so that they can train in an interdisciplinary fashion and be I wouldn't say deaf but not broadly familiar with topics across disciplines to inform their research choices. So our theme, we called our program Energize, and it's about energy and materials. And we have students in our program from the chemistry department, physics, in the arts and sciences unit. We have students from engineering and various disciplines, and hopefully we're also going to get people from data science, from CDS. But we do have faculty partners who are working across all of those disciplines. And the goal is to actually train the students to get outside of the box and stop just thinking about their small piece of the types of projects that they can solve in this space, but to also think about how it interrelates. For our data scientists to think about how they can inform and experiment, and for our measuring, people who do measurements to think about how they can actually get extra information. And so in addition to doing research, our students also doing a lot of workshops. We're helping them become better science communicators, policy, and things like that that are in the nature that are going to occur. Each student's in the program for 2 years, and so we'll cycle out, we'll bring a new cohort who'll start year 1. This group will be year 2. And one of the things we make our students do is to organize this symposia. So we're really excited because this is the first one. Next year, you guys will be the experienced group to help the new group get through this, but so far, so good. So without further delay, I'm going to hand the mic over, and we're going to introduce our very first speaker today. We have a wonderful lineup of speakers, a great complement of posters on student research as well, and some excellent networking opportunities. And lastly, I'd just be remiss if I say thank you to all our visitors from other campuses who came here today to participate in this with us. Enjoy your time.
Hello. It is my pleasure to introduce Peter Schindler from Northeastern University, where he's an assistant professor in mechanical industrial engineering and leads the Data-Driven Renewables Research Group. Dr. Schindler research focuses on discovering and understanding novel materials for energy applications through high-throughput quantum chemistry calculations and data-driven predictions of materials properties. His work directly aligns with the theme of this symposium on data-driven discovery and energy materials, highlighting how computational and machine learning approaches can accelerate materials innovation. He is also the recipient of the prestigious Erwin Schrödinger Fellowship. Please join me in welcoming Dr. Peter Schindler.
Thanks so much for the kind introduction. I don't want to hide behind the podium. I'm kind of a walker, so I hope I speak loudly enough for the audience to hear me. It's pretty amazing to be here. What a view. And I don't mean myself, but the view of Boston is quite nice. Today I'm trying to answer the question, can we actually discover... Oh, I see. Okay. Can we actually discover new materials with a computer? And it goes back to this very old quote from Dr. Box. All models are wrong, but some are useful. And today I'm trying to answer, within computational material science, how wrong are the models and how useful are they? And there's a specific trade-off within computational material science. There's different modeling tools you can pick based on how accurate you want those predictions to be, and which kind of length and time scales you want to model. And that trade-off comes from the fact that the more accurate you get in your computational method, the more computationally expensive it is to run these computations. And so in the bottom left, you have a quantum chemistry calculation, density functional theory, DFT, or even slightly more accurate versions of that. And then if you go up to molecular dynamics and then all the way up to mechanical engineering, finite element modeling, you become less accurate and more kind of qualitative in nature as you predict those properties. But maybe one question for the audience: who has used any of these computational methods before? Okay, quite a lot. Who has used density functional theory or, okay. Who has run density functional theory of 100 atoms? 200 atoms? 500 atoms? Wow, okay, there's some people left. 1,000 atoms? Okay. But that was gamma only, right? I'm assuming 1,000. Yeah, so probably as you go to higher kind of length scales, it will become prohibitive to run density functional theory, just for the nature of how expensive it is to run these computations. But nonetheless, all of these methods are quite a bit faster than running experiments, as you would guess. So experiments, for the experimentalists in this audience, if you synthesize materials, that can typically take weeks to months, and in some cases, an entire PhD to synthesize a single material. And then first principles calculations, on the other hand, typically take hours to days on a supercomputer, and in maybe worst case scenarios, if you run 1,000 atoms, it can take maybe weeks on a high performance computer. But even though that's quite a bit faster than experiments, that is still too slow if you screen through a space that has hundreds of thousands or millions of possible candidates. And that's where now the fourth paradigm of science enters, the data-driven modeling, where you rely on previous databases of materials properties that were computed with these computational methods. And you try now to learn the relationship between the structure and the property. So you have input crystal structures, and you try to predict a certain computed property, but using a data set as a learning tool. And that usually involves two steps. First, you need to think about how can you actually featureize materials. So how can you represent a crystal structure as a numeric object that the machine learning model understands. And then as a second part, you plug that numeric representation into a learning model. And it turns out students are always very excited to do AI and machine learning in material science. It turns out most of the work is actually done on the data set side and on the choice of how you featureize your problem. That's actually the hard part. The easy part is running the machine learning model itself, because that's just a couple lines of Python code from scikit-learn or PyTorch, and then you can do machine learning. So that we'll discuss today, a little bit about myself and my group. So my background is a bit unique. I started actually as an experimentalist. I'm a physicist by training, but I did thin film deposition techniques. And then during my postdoctoral research, I switched over to first principles modeling. And then just before joining Northeastern as a faculty, I was a little time at a startup called Aeonics. So they do basically materials informatics for battery materials specifically. So that is kind of a more kind of nonlinear career path, maybe, I would say, but that's what my research nowadays focuses on at the Data-Driven Renewables Research Group, or D2R2. And also inspired on a post on LinkedIn, I want to make academia a little bit more accessible or like kind of personable. So I share some private information as well. So I have an almost 2-year-old daughter now who is jet-lagged from our travel. So I'm also a bit tired today. But yeah, feel free to chat with me about any of the other topics I mentioned here. Maybe it makes it easier to approach me during the poster session. So I'll have 2 parts today. So the first part, I will explain a bit what universal machine learning interatomic potentials are. So this is more educational to give you some context what those can potentially do. And then in the second part, I will apply those to surface properties of materials, which my group is specifically interested in, and how that relates to properties important for renewable energy applications. And so the promise of these MLIPs, or recently, that's kind of a mouthful, so another alternative name. There are many names, actually, machine learning force fields and so on. The recent one is foundational interatomic potentials. You can pick your favorite one. So the promise is if you have a lot of data on the bottom left corner, so you have a lot of data that describes, let's say, molecules or materials on the quantum chemistry level, what if we train interatomic potentials on this data, which makes it easier to run then and enables much larger time and length scales at near first principles accuracy. So that's the promise. So let's talk about this. How does this compare to conventional molecular dynamics? For the ones who are familiar with this, so you basically pick an atomic arrangement, and then you parameterize the potential energy by a function, for example, the Lennard-Jones potential, which you probably have heard of, and then you fit those two parameters, I guess sigma and the other one, based on your system. And maybe you know that the Lennard-Jones potential works pretty well for noble gases, but I wouldn't trust it, let's say, for a metal or a semiconductor or oxide. It will probably not work well to use the Lennard-Jones potential. So you fit this empirically and predict the individual energies of all the atoms. And then if you sum up all the contributions, you get the total energy of your system. And more so, if you take the derivative of that potential energy, you also get the forces on each of the atoms. And if you know the forces, you can do Newtonian mechanics and evolve the system at a specific temperature or relaxation. Again, this works well. This is easy to compute, these kind of functional forms, but they're highly restrictive on which kind of system those fitted parameters actually work on. And so the alternative approach now is using the machine learning interatomic potentials. It looks very similar, so you start with the same atomic arrangement, but you then featureize that arrangement. Let's say it could be a graph representation or some other fingerprint of the structure, and that numeric representation I put into a neural network architecture, which has, of course, many, many parameters to tune, so it's highly nonlinear and highly flexible. And then I can learn any sort of representation of the energy given any configuration of atoms. So this is much more flexible than the left side approach, but of course requires data that you need to train these weights of the neural network on. And so a little bit about the kind of history of the MLIPs. Actually, last semester I taught a special topics course called Machine Learning for Material Science and Discovery, and there I go into great length of the entire history of MLIPs. I'll start, for today, I only tell the kind of most recent years from 2023 to today. The new term moved away from machine learning force field towards the new word universal MLIPs, or foundational interatomic potentials. The promise here is universal in the sense this machine learning interatomic potential can be applied across the entire periodic table. That's the promise. We'll see if that actually holds true. And enabled was this partially due to new architecture, so equivariant graph neural networks, but more importantly was enabled by new very large data sets of ab initio calculated properties. So it started with the OC20 Open Catalyst data set with surfaces, then moved over to MPTRAS, so Materials Project, which was around 1.6 million data points. But I think the real game changer then was Alexandria with 5 million data points, and then lastly OMAT24 by Meta, so former Facebook. That one is now orders of magnitude larger, so we have reached domains where we have 10 to the 8 data points, so of the order of 100 million data points at quantum accuracy. And of course, that justifies more the question that, yeah, a question? So this is all DFT calculated bulk structures. Across the periodic table, PBE level, plus U for certain oxides, yeah. So this is DFT calculated, just bulk structures, no surfaces, no low-dimensional materials, but they include bulk structures that are distorted, so lattice strain, and high temperature molecular dynamics ab initio simulations. So, and it turns out actually these non-equilibrium structures are the main benefit of generalizing well to unseen configurations, as we will see. Okay, and so if we now assume we have such a machine learning interatomic potential that's universal, again, asterisks, we'll see, is that actually true on the PBE level? What can we do with that? And so I think that enables quite a lot of things. So instead of the conventional data-driven approach, so given an input structure, you try to predict a property in a kind of black box machine learning fashion. In this case, I'm giving you as an example the bulk modulus of a bulk crystal structure. So the top version is basically the conventional approach. The bottom approach is now enabled by machine learning interatomic potentials. So if I take a crystal structure and I strain it different amounts, and then for each of the strained versions of the bulk structure, I predict the total energy of the system, and then I plot that total energy as a function of the unit cell volume, and I fit an equation of state, so a quadratic function. The factor in front of the quadratic term is, in fact, the bulk modulus. So this is a physics-based. So going from this plot to the bulk modulus is a physics-motivated step. And the interesting part in the lower part, if you assume you have a universal potential, no new training was required here. So I didn't even need a data set that connects the input structure to the bulk modulus. So this is a property that is so-called derived from the potential energy surface. And that, of course, if we trust that we have such a potential, that enables us quite powerful predictions of material properties without any new training. In fact, there's a few properties that can be derived from the potential energy surface. That's thermodynamic properties, mechanical properties, and what I'm mostly interested in, surface energy, which I will discuss specifically. And there's a new package that kind of wraps around different machine learning interatomic potentials and can predict those very easily. It's called MatCalc by the same developer as PyMagen. Yeah. Well, actually for this one, no, but for, let's say, phonons, yes. Yes, for phonons, definitely, yeah. So actually, we'll get to that in a second, but for total energy, you actually don't, the derivative is not as impactful, but for phonons, the displacements, yes, exactly, yeah, yep. And so I made that asterisk, so how universal are those potentials? Well, we shouldn't trust that people say it's universal. We should actually benchmark if that's the case. So there's two large benchmarking efforts. One is called the MatBench Discovery by Janusz Ribesel, and the other one is the MLIP Arena Leaderboard by Yuan Jiang. So those two benchmark slightly different properties, but actually the left one actually does, for example, the most challenging target here is actually the thermal conductivity, which includes phonon predictions. And those historically with the older MLIPs really underperformed, but the most recent ones actually made a quite large stride towards also being able to predict phonon-related properties. And the MLIP Arena is a little bit more focused on physical prediction, as in it looks at two atomic displacement curves if they look like an interatomic potential, and some stability concerns, how many steps of MD it is mostly stable for before, let's say, predicting unphysical steps or exploding the simulation. So slightly different scope, but important to actually measure how do these most recent MLIPs actually perform on real world targets. However, both of those are missing targets on surface-related properties, and that's hopefully where my group added a little bit of new information to the field. But before we go to the surface-related things, I always like to bring up this slide, especially for students. So all I'm saying here, materials informatics, AI for materials, is that like some academic pursuit that's completely irrelevant to industry. And I guess we'll hear from the industry panel later. I'm curious to hear from them as well. But I think the answer is no, this is not only for academia, this is also for industry. So actually all larger companies, let's say in the tech sector, so Meta, Microsoft, NVIDIA more recently, they have entered the materials informatics domain. Actually, maybe, I mean, not super important, but maybe we can turn off this slide because it washes out the, but it's generally bright, so I guess maybe that does make a big difference. So yeah, all the big companies are in there. NVIDIA most recently joined with NVIDIA Alchemy, so they started a new team on materials informatics. But I think even more important, maybe the crazy stuff, there's a whole sea of startups in that specific domain that try to do AI for either chemistry or materials, or partially biochemistry as well. So there's many of those, and a lot of those actually also got large runs of seed funding or Series A funding. So there's definitely promise in this field. We'll see where it goes. It could be a hype, and we'll learn which of these companies actually succeed in that domain. But it's an exciting time to be in materials informatics, I guess. Okay. So now for the second part, let's apply this a little bit to what my group is interested in, and that is we're interested in finding new stable surfaces that have tailored work functions. And I'll explain what surface energy and work function means and why that is important. So first of all, surface or cleavage energy is the energy difference between a cleaved slab and the bulk divided by the surface area, and it basically determines the surface stability. And if you have heard of that, it also determines the so-called valve construction. That's the right object here. That is basically a 0th order approximation of how a nanoparticle would look like if it's suspended and has no other influences from the outside. And of course, as you probably would guess, the stability of a surface is critical for things like crack propagation, catalysis, adhesion, absorption, this kind of surface-mediated processes. And the second property, you maybe have also heard of it, is called the work function. So how much energy is required to extract an electron from the surface. So photoelectric effect, Nobel Prize, if you have heard of this. So in solid state physics terms, that's the energy difference between the energy at the vacuum level with respect to the Fermi level inside the material. And of course, you can probably appreciate that this is important for various applications. One of them is the less known cousin of the thermoelectric converter, the thermionic energy converter. So that tries to harvest waste heat and convert that heat back into usable electricity. And the work function, of course, matters here because it determines how easily you can actually extract electrons from in this side, actually the cold side. And it's also important for transistors and DRAM. So the work function will determine the contact barrier in a metal semiconductor interface or semiconductor-semiconductor interface and so on. And so it's important for photocathodes, but also photovoltaics and generally electron emission devices. Okay, so as said before, these surface properties were not benchmarked on these two large benchmarking efforts. And so we changed that, hopefully, by the cleavage energy is, in fact, a property that can be directly derived from the potential energy surface by predicting the total energy of the slab and predicting the total energy of the bulk separately, and then plugging those predictions into that equation gives you directly the cleavage energy. And we looked at 19 most recent state-of-the-art MLIPs and compared it to the PBE level density functional theory ground truth. That's based on an earlier work of mine during the last years of my postdoc, where we created a data set of around 60,000 work functions and around 34,000 cleavage energies. And then after we do this, of course, after we compare to the ground truth, we then rank them, how well are they actually performing without having seen the surface data set. And to my surprise, when I started this project, I was highly critical of the prospects of such a, like using MLIP without additional training to predict those properties. I was skeptical of that, but I was proved wrong, I guess, because the top models, like the most recent ones, like UMA, UMA, or ESEN, or Equiformer V2, trained on these OMAT 24 data set that I mentioned before, they perform surprisingly well. So it has like a median error of 1.3% only. And it also gets, so this green bar is saying that in 90% of the cases, it can recover the most stable surface among all competing surfaces. So giving a single bulk structure, if you look at all the surface energies of the low index cuts, it can successfully identify the one that is most stable among all of them. So that was kind of surprising to me because I want to stress again, this was not trained on this surface data set. This was taking universal MLIPs that have never seen a surface data set before and predicting these surface properties directly through the potential energy surface. So that's quite remarkable when I saw this first. And here's some more detailed like results, but I think most important, we can see if we stay in the same architecture, so Equiformer V2, for example, it matters drastically which training set was used for the MLIP training. So if you use OC20, which was a much older data set, just on surfaces, surprisingly, it contains surfaces only, but it does not now perform nearly as well as the other more recent MLIPs that are trained on OMAT24. So it's more than 10 times higher error compared to the OMAT24 dataset trained. But the architecture matters too, not as much for the performance of the error, but it does matter in terms of the prediction speed. So the Grace model, which is quite a more lightweight version of an MLIP, predicts now in a fraction of the time required to predict with Equiformer V2. So the architecture matters not as much for the accuracy of the prediction, but it matters drastically for the inference speed. So how quickly can I predict those properties? And then now slightly changing gears, I will not go into great detail on this graph neural network approach. This one is not related to MLIPs, but I have actually another talk coming up tomorrow at 3 p.m. In the MSc talks, so Material Science Department. There I'll have a little bit more time to spend on explaining what equivariant graph neural networks are and what we have changed here to predict the work function, because the work function, unlike the cleavage energy, is an electronic structure property, and the MLIP cannot help us there. So MLIPs only can calculate basically total energies and forces, but that doesn't get you to a band gap or any electronic structure information. So we started with a similar approach. So we made a graph-based representation of the slabs. Then we concatenate the individual forces with ORB3. That is, in fact, the MLIP. So we do use MLIPs in this new architecture and concatenate that with the feature representation of the nodes. Then we do an equivariant projection. Again, I'm not going into detail here, but if you're curious about that, you can join me tomorrow at 3. And then concatenate the absolute C coordinate. And the reason is we believe that for a surface property, one of the directions is actually symmetry broken. That's the direction normal to the surface. So we think that breaking the full E3 symmetry is here beneficial to get improved performance. And then we do the remaining graph neural network and pooling steps to then, at the end of it, predict work functions and cleavage energies. And just to briefly show you the results, so the green bar is a random forest model of my earlier work that was basically a hand-featurized approach, which was the state-of-the-art model back then in 24. And then on the very right, where the error is, that is the new FIRE GNN architecture I just mentioned, with and without that symmetry breaking. And you do, in fact, see an improvement if you add symmetry breaking to that architecture. And that, with the force information and the symmetry breaking, outperforms the previous state-of-the-art in predicting the work function. And then, lastly, before we go to the kind of challenges of the field, I heard also some questions that were already challenging. I'll bring those up again. One more thing that is often overlooked in material science or AI for material science is we should care about actually not the in-distribution error. So if you randomly split your data into training and test, and if you do so randomly, that is so-called in-distribution performance or generalizability. We should actually care more about out-of-distribution generalizability. So how does the model do on data that is outside of the training set scope? And we developed a package for that called Matfold. So that makes it easy for you to split, let's say, an entire chemical element you hold out into the test set. So the training set is a certain chemical space that does not include the specific element. And then in the test set, you're testing now, how does it perform on this unseen element? Or you can also do a space group or an entire periodic table group. So this package, Python, is very easy to install. You can play around with it in an interactive Google Colab notebook, if you so please. And yeah, so this makes it easy to test that. And for that Phi GNN, we did those splits. So the leftmost is basically the random split. And then here I'm holding out an entire space group, an entire element, or even an entire periodic table group. And with the graph neural network, we then see not only does it improve in terms of the random in-distribution performance, it also improves in the out-of-distribution performance. So if you hold out a space group, it reduces the error by 30%. And if you hold out an element, the benefit is less pronounced. It is minus 15% only. We believe that structural generalization is better for graph-based approaches than, let's say, hand-picked featureizers, which are already based on elemental representations. And if you very challenging out-of-distribution splits, so where you hold out an entire periodic table group, is actually basically there's no more benefit of this model. Okay, so I was asked by the organizers to, actually I forgot, I have one more slide. So what have we used this for? These kind of approaches and the surface-based modeling is we used it again to discover these extreme work function materials, so ones that are extremely low or extremely high. The ones who have an extremely low work function are important for electron emission devices, whereas the ones that are extremely high is important for DRAM and transistor applications. And we want also ones that have a very low cleavage energy, so they are stable. And so we have discovered some of those, and then we applied this also to discovery of air-stable photocathode materials. For that, we needed to develop also a fully ab initio model of the electron emission process in a photocathode. And then lastly, we also use this for screening through adhesion parameters in battery interfaces. Okay, but now the last slide for today. So what are the now future challenges and opportunities in this field? So first of all, so the question I asked in the beginning, can we discover new materials with a computer? I hope I convinced you that, that these predicting surface properties is quite reliable with AI. And the other thing is also AI is actually computationally significantly cheaper compared to the ground truth first principles calculations, with the caveat, of course, that the initial training set is expensive to compute. But once you have large training sets, the training of AI models is moderately expensive, but the inference time when you use a model is very cheap. So that's why you can scale up the screening so much. So did I convince you that we can discover materials? Well, not quite maybe. So there's a few issues here, I think, that stay unaddressed. So the first one is actually the question, what is a material in a computational setting, is somewhat reductive. So oftentimes in my community, materials informatics, materials are represented as perfect single crystals. So that's pretty common. Materials project, all the large data sets have a wide range of bulk structures that are crystal structures from the ICSD originally. But of course, in real life, materials have a microstructure. They have disorder. Processing conditions will affect all of these. And defects, surfaces, all these effects will, of course, translate to different properties in real life. And on top of that, I think this was brought up earlier, well, the typical level of theory chosen, in many cases PBE, is often insufficient. So PBE, for example, for transition metal oxides or F-block elements is highly unreliable because the electrons are very localized in those materials. And so if you do a wide screening across the periodic table, but you just across the board assume PBE, I think that leads to certain issues, especially for specific material properties, where this is not a good assumption. And so the ground truth, even though the model has a very low error, what you're predicting is a value that is not useful, right? Because the ground truth information is not useful. And so these two combined lead to quite a drastic gap between first principles predictions in some case and the actual experimental validation of such. I think MLIPs, however, as an opportunity for that, can partially maybe close this gap, again, through accessing large time and length scales, but also for systematic kind of studies. It could it could help that at least partially. For example, in my data set that I showed earlier, I have work functions and cleavage energies of surfaces. The assumption here is that is perfectly cleaved milli-index planes, which is also not true. Surfaces are rough. They're like more complicated than the naive cut. And so MLIPs can go beyond that by now modeling much larger unit cells that have like roughness incorporated. That's an example. And then this one I heard in just a couple weeks ago at TMS in San Diego by Professor Billinger. I haven't thought about this before, but it is actually true. There's a bias towards fair data sets. And for the ones who don't know, fair means findable, accessible, interoperable, and reproducible, which of course we should make data fair. We should make it easy accessible. But it turns out the machine learning community will always jump on the data sets that are exclusively fair. Or in other words, we bias the entire system towards data sets that are most easy to compute or most easy to access. Which of course is an inherent bias because the ones that are tricky to compute or to assess are not studied, right? Or on the flip side, industry is usually not interested in those niche data sets to make them fair. So they make it proprietary for good reason, I guess. So we cannot use that in academia. Okay, so that's it for me. So thanks so much to my group and to my collaborators. Also thanks so much for the organizers, Jesse and Jonathan, for reaching out and inviting me. And so I'm happy to answer any questions.
I think we should have time for like 1 or 2 questions. We have some microphones going out.
I guess for the recording.
Hey, that was a really very interesting talk. And so just wanted to ask one question about the surfaces. I think that's a very interesting finding because the training set doesn't maybe necessarily at first glance contain under-coordinated atoms in bonding environments, but it sounds like it contains enough heterogeneous boundary environments to get this right. I'm wondering though about that, I think 90% is a pretty successful study on this regard, but what about the 10% where it doesn't work as well? And are there any systematics? Are there kinds of materials or certain kinds of surfaces that are more prone to fail with these potentials? I'm just curious.
First, the observation, we made a similar kind of highlight of that observation that it does translate to surfaces. I think the reason we believe in the OMAD24 data set is it has enough distorted structures that it can, so it has not necessarily bond breaking captured maybe, but bond stretching, and that is enough to translate to broken bonds at the surface. I was surprised too, but it works actually pretty well. For the second part of the question, actually we studied a lot of those questions in detail in the paper as well. But from what I remember is that specifically fluorine-containing surfaces were really poorly, fluorine chemistry is complicated, I guess. So I think where the ground truth is also, I guess, uncertain of and underrepresented in the training data set potentially is also not well predicted in this study. I guess, most likely. And there was also like a slight systematic shift, if I remember correctly, towards lower cleavage energy. So there's a slight, if you plot the residuals, there's a slight, it's not exactly at 0, that bell curve, it's slightly to the left, but very slightly. So there's a slight underestimation bias.
Great talk, thanks.
Thanks so much.
I might have missed it, but in order to calculate the work functions, these are electronic properties, serious electronic properties, where you're actually ripping an electron off of a surface, right? And so what are you training on in order to actually
So basically that data set I created earlier, that was based on PBE level DFT. And so the way you do that is you just cleave the surface, and then you actually have to apply dipole correction, and then you can measure vacuum energy level in the vacuum region, and you get also the Fermi level from the DFT calculation. That difference is the work function. One maybe important point related to your question is, in the initial generation of that data set, I restricted myself to materials that have an almost zero band gap. Because it turns out, if you know, DFT is very, well, PBE level DFT is very bad at predicting the band gap. So similarly, the Fermi level is in the center of the gap. The expectation is that the Fermi level of semiconductors is also not well predicted. So I restricted myself to metallic or close to metallic compounds. Yeah, this was trained specifically on the work function.
So it's not just energy forces in that case.
No, and not in that case. Yeah, that's the big distinction, is that the MLIPs only give you properties that are directly derived from the potential energy surface, i.e. it based on total energies or forces, but not like you cannot predict the band gap or work function. Yeah. Right. That is separately trained.
Thank you very much.
Thanks so much for the questions.
Dr. Schindler again. I don't know if this is on. Okay, cool. So, I'm good. Okay. While we are setting up the next presentation, it is my pleasure to introduce Professor Pankaj Mehta from Boston University, where he's a professor of physics. Professor Mehta is a theoretical physicist whose research explores the interface of physics, biology, and machine learning. His work draws on tools from statistical physics to understand how complex collective behaviors emerge in high-dimensional, data-rich systems, from cellular decision-making to modern machine learning models. His research aligns closely with the theme of the symposium on data-driven discovery, highlighting how physics-based frameworks can provide deep insight into complex, data-intensive problems. Professor Mehta received numerous awards, including being named a Fellow of the American Physical Society, a Simmons Investigator in the Mechanical Modeling of Living Systems, and an Alfred P. Sloan Research Fellow. Please join me in welcoming Professor Mehta.
Well, thank you for having me. I'm really an outsider. I don't think I align pretty well at all. I haven't thought about materials since Jeff's office was across from me when I was a graduate student. I'm mostly a biophysicist. So, you know, I was like, I'm a biological physicist. I'm really interested in biology much more than machine learning, like a lot more. So why am I giving this talk to a bunch of materials scientists interested in energy? And I think the real reason is, like, I like teaching people stuff and learning stuff. So like about 10 years ago, we started writing this review, which I think was influential to a lot of physicists because there was very little material. There was very little about machine learning from a physics point of view. And you know, what's fun about this talk, and I think the other reason I'm here is because I've taught a lot of people, of the students in the room, is the review holds up reasonably well, but there's one fundamental thing it got wrong. And the fundamental thing it got wrong is that when I was a graduate student, you know, and a postdoc, and an early faculty member, you know, basically until 5-7 years ago, you know, I was taught this thing by von Neumann. And this was the quote that, you know, every physicist, this was drilled into our head. You know, with 4 parameters, I could fit an elephant, and with 5, I can make him wiggle his trunk. And there's this amazing, even American Journal of Physics paper from 2010, which is not that long ago. Okay, for the young kids, it's a long time ago. I guess I'm solidly in middle age now, so. But it was very cute, right? I mean, this was a thing that we all taught everyone before the last 10, 15 years. Don't use a lot of parameters. And the thing that confused me, because I've been teaching this machine learning class since about 2015 or very early for physicists, right? Is that, and this is something that, you know, a lot of people started thinking about, but like you went in 2015 when I was basically teaching this machine learning class, when I first started writing that review, and you go to this very famous classification thing. So this talk's gonna have nothing to do with materials. It's gonna have a lot to do with me being confused about machine learning for about 10 years and then doing stuff to try to figure it out, and me trying to explain to you some very basic stuff that, in my opinion, is not explained well anywhere, okay? So I apologize, no materials. Just some crap about regression, okay? Not even any AI, just regression. All right. So, but I guess the motivation is this, which is that you go, and this is, forget modern large language models. Let's do something closer to the kind of neural networks you guys are using in material science, which are just like forward MLPs with many layers. And the funny thing is that, you have this thing like the ImageNet classification challenge. You have 1,000 classes, 1.2 million training images. And then you go to the leaderboard. This is probably from like 3-4 years ago, but it hasn't changed that much. And you go and you say, look at the accuracy, and then you look at the number of parameters, right? And the number of parameters are like 100 million. So you're like, what happened to von Neumann? How come I can fit 1.2 trillion images and use 100 million images, 100 million parameters? And the person who actually, I think popularized this the most is this guy Ben Recht, who's at Berkeley. He has an amazing book that just called The Irrational Decision that he just released, a popular book. I recommend everyone read it. It's quite outstanding. And they had this famous paper that said understanding deep learning requires rethinking generalization, because they basically took one of these neural networks, right, that could do ImageNet, and what they did was they basically showed that it was expressive enough to fit random noise. So you just took random noise, you trained it on the same architecture, and there were enough parameters to fit random noise and get zero training error. Of course, zero test error as well. I mean, infinite test error, but zero training error. And so there's something fundamentally about statistics that was missing in all this, right? And I apologize for the students who already saw this in class, but you guys made me come ask. I would have never volunteered to give a talk otherwise. So this is basically a little thing where we did a lot of very, very fancy replica and random matrix theory calculations and lots of fancy math, but you're not going to see any of that. What you're going to learn is what I wanted to understand, which is like I wanted to have a simple understanding, the simplest possible understanding of what we got wrong about statistics, why statistics still works, even if you have many more parameters than data points. And in the process, maybe we can understand basically what machine learning can and can't do, because there's a lot of fancy claims about what's going on. So please ask me questions. If many of you have sat through talks with me in the audience or seen a question, you know that I am incapable of not asking questions, and I get nervous when people are not asking me questions. So interrupt me. I like interruptions. That's the way I function. There's no reason I have to get through all this. And the next 5 slides will tell you basically what you have to know, all right? So I think, again, this is what I want to understand. With 4 parameters, I can fit an elephant. With 5, I can make his wiggle his trunk. For 100 years, people believe this was true. It turns out to be completely wrong. And everyone pretends it's not a big deal, but I couldn't accept that, and I didn't like anyone's explanations. So, here's a simple example. Here's an example that has nothing to do with with regression. This is an example that all of you think you understand. And maybe many of you have seen this, right? So here's polynomial regression. How complicated a model should I use, right? This is what I was taught, always. So here we go. So the basic idea is, right, I want to think about model complexity. In polynomial regression, it's easy. It's the number of terms I'm using. And then I'm going to try to show you on the right some training data, some test data, and the model's prediction. And I'm going to do training and test error, right? I'm going to assume you guys know what that is. Training data points are the data I use to fit the model. Test data points are points that are generated from the same distribution, but I didn't use to fit the model. And there's always a gap between those. So this is what I learned in statistics class, and this is what I learned in physics class. All right, you increase the model complexity, I do better. Wonderful. I increase the model complexity some more. At some point, I get enough parameters to fit all the training data, and the training error goes to 0. But the test error, I messed up these slides somehow, right? The test error gets much, much worse, right? So the basic idea is this is basically what we learned about modern statistics, right? Oh, I skipped a slide, that's why. I do this, I get more expressive, I get better. I even put more things, training error goes to 0, my test error goes away, and I have this U-shaped curve, right? So everyone's like, use the right number of parameters because things are going to get bad if I use too many parameters because I overfit. And this point here where I have exactly enough parameters to fit all the training data point is going to play a special role. It's called the interpolation threshold, for reasons that are going to become clear because something qualitatively different happens. And there, the training error goes to 0. Right? And so the idea, like, what von Neumann was trying to tell us is that we should use something with optimal complexities that sits in the middle. And often this is talked about in what I find to be the most interesting way to think about it, which is in the bias-variance trade-off. So bias is the tendency to underfit. It's the inability to express relationships underlying the data. And variance is the tendency to overfit. It's to memorize the details of the training data that are not generalizable. And of course, what happens is in this regime, the bias goes down, the variance goes up, and because you're balancing bias and variance, things, the test error, you should use it at optimal complexity. But this is the fun thing. Again, bias is the tendency to overfit, variance is the tendency to overfit. And the question I wanted to ask, and I just didn't know, I was teaching this class every semester, or every other year, and every year, and I was like, I don't understand. So I went and read a bunch of literature, and I still didn't understand, and I don't like when I don't understand things. I found that if people can't give me a clear answer, often they just don't know it. So the funny thing is, you do this with polynomial regression. This is the moment where we started getting interested. And I just, for some stupid reason, just keep increasing the number of data parameters. Oh, that function looks a little better. And I keep on increasing the number of data points. And that function looks a little better. I've put a tiny bit of regularization in here, just to be honest. And you keep on doing this, and look. Actually, even in polynomial regression, it's actually not true. You actually do better as I use more parameters. What's going on? Well, we can just look by I. What's going on with I is that you're like just making little bumps around the training data set, and you look like you're interpolating the function, right? You've gone from a regime from statistical fitting to a regime of interpolation, right? I just put little Gaussian widths around these things. In principle, without regularization, you'd have delta function peaks, but you just regularize them. And so this was something that was popularized by Misha Belkin at UCSD. He basically showed that it's actually a very generic behavior of all statistical models. And he did it empirically. So there's a series of PNAS papers there and some other papers. And so, so he had this very nice paper where he did random forests, MLPs, all these kind of weird problems. And he said, how do we reconcile modern machine learning practice in the classic bias variance trade-off? And now it's like a giant industry of works, right? And what's funny is that this kind of double descent behavior is actually known from the 80s. People just ignored it, right? It's in this very classic book on statistical learning. And so the question we wanted to ask is, how do we understand this? So it's there in polynomial regression. It's not something that's special about machine learning. It just somehow has been missed by statistics for 100 years. And so what we wanted to understand is, of course, the classic way I like to think about these models is in terms of bias and variance. You underfit, you overfit. We know what the bias and variance does. So, variance goes up, bias goes down. You make this U-shaped curve, and we wanted to understand what happens on the other side. Yeah, go ahead. Grokking is, I think, a much more complicated phenomenon than this. Yeah, no, I'm not going to even fit anything with stochastic gradient descent. This is all deterministic L2. I'm going to do it in the simplest setting, because everyone says this is something about fancy machine learning. No, I'm doing ridgeless regression. I'm doing regression. I'm not using SGD. So I think the real answer is that they're different phenomenon. Grokking is, I don't know how much modern machine learning you know, but there's essentially this idea of lazy regimes and feature learning regimes. So the idea is whether when your model gets big enough, are you really learning meaningful features, or are you learning a fixed kernel? So when you're learning a fixed kernel, that's called the lazy regime. When you really learn meaningful features, that's called feature learning. So the Grokking transition seems to be much more a transition between lazy and feature learning. And this is just a phenomenon you see in L2, I invert a matrix, no stochastic gradient descents, lazy learning. No, I had no learning rate. There's no learning rate. This is just fit parameters. There's no learning rate. There's no learning rate anywhere in here. It's completely deterministic, nothing stochastic. There is nothing complicated about it. It's a regression. Yeah, thanks for asking the question. I have no reason I have to get through stuff. I basically told you everything I need to tell you. All right. So what we wanted to do was do this in the simplest setting possible. And I mean, it's simple in the setting. The math was quite, it has a 50-page supplementary information. So it's like a crazy dynamical mean field theory, random matrix theory calculation, but you're not going to see any of it. But the basic idea was, let's do this in the dumbest place possible, which is basically some versions of regression. So we had these two models. One was a linear regression model, where we just, I think everyone understands linear regression. The second model was this model where we made a 2-layer neural network, but it's not really a neural network at all. What it is it's like a nonlinear function followed by regression. All right, so we're only training the top layer, the bottom layer is fixed. And the point was that everyone tells you it has something to do with stochastic gradient descent or something fancy about machine learning. We're not doing any of that. We're just doing ridgeless regression. So we just take a pseudo-inverse, like you were taught in your first day of statistics, and we just calculate the pseudo-inverse. That's how we fit all this. So nothing complicated going on. So for experts, it's lazy learning regime, deterministic solution, trivial training dynamics, trivial solution landscape. There's not many minima. None of the stuff people say is the reason this happens and it occurs in these models, right? No minima, no stochastic gradient descent, lazy learning, blah, blah, blah. So, so what we wanted to understand is, so this is this second model that I showed you where I have a random linear model, and if I just do some things, I look at the number of parameters and look at the amount of data. You have two regimes, the underparameterized, where data is greater than parameters, overparameterized, where the parameters are greater than data, and as usual, you see the test error spikes up, goes down, and there's a phase transition exactly where the training error goes to 0. So what we wanted to understand is what happens to the bias and variance trade-off, right? So this is just showing you we can calculate some stuff. And that regression looks different from this two-feature learning thing for reasons that we probably won't have time based on how slow I'm talking. And so what we wanted to understand is what happens to the bias and the variance, right? And so what we wanted to understand, again, I'll just go here, is what happens to the bias and variance. And so you can do some calculations. And what you can see is that on the left-hand side, you have this classic U-shape. If I look on the right, you can see the bias is in green. That variance is in purple. And what you can see is that I have this classic U-shaped curve on the left-hand side in the underparameterized regime. And as you expect, it happens because the bias goes down, and the variance, which is how much I'm overfitting the particular data set I look at, actually goes up. But then if you do the proper calculations, there's a lot of wrong calculations in the literature, actually, or they calculate the wrong quantity and call it variance. That's the way, and bias. That's the way I would say it. Is that you see that actually something very funny happens. So remember, bias is about how expressive the model is. So as you increase the number of parameters, the bias keeps going down, 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 as you'd express, because the model is getting more expressive. But a very funny thing happens with the variance, which is that it goes up, which means that as I get close to exactly having as many data points as parameters, I get very idiosyncratic about the data points. I overfit. But then as I increase the number of parameters, I stop overfitting. All right, so the variance goes back down. And the question is why? Let's have some intuitions. So basically, if you take away nothing else from this, you should never work in that middle region. Right? You should never work in that middle region. Right? And you should also take away that on the right-hand side, I'm doing something different. I'm interpolating. And that's actually what I think your materials, metamaterials thing is about. I have one data set, I have another data set, let me interpolate them. You know, so what's going on? So here is, I have 5 minutes, so I think, how much time do I have? When am I done? 5 minutes? Okay. I have 5 minutes, I think. I'll give myself 5 minutes. Everyone's tired. So the basic idea is that I'm doing regression, and what I should think about is doing some kernel regression. So I have some y hat is some kernel, like some internal representation of the model, which I'm calling z, times some parameters. And I can ask, how is the model internally representing the data? And one way I can do that is I can just do a PCA, basically make a scatter plot, and fit an ellipse to the internal representation of the model. Right? So I have z. And then the interesting thing is that this z is, of course, how the model views the data. And the eigenvalues, right, of this are basically telling you how well the directions are sampled. All right? So it says, this direction is much more well sampled in the model's internal space than this one is sampled. And so we want to really understand, how can we understand this in a very intuitive way? So like I said, we did a lot of painful calculations, but I'm sparing you those. And you can see they worked. You see the lines and the numerics fit on top of each other. We're very proud of those. All right, so here is what happens. So I'm showing you the eigenvalues in different places. So I'm here in the underparameterized regime here. On the left-hand side, you see the arrow over there. And what you can see is that if I look at the eigenvalues, there's a big, big gap. All the features are well sampled, and the model makes good predictions. So that's the minimum on the left. If I, on the other hand, get near this interpolation threshold, something interesting happens. The gap actually closes. And what happens is that you have the well-sampled features, but I also have lots of poorly sampled features. And what happens is the reason you overfit is that I put too much weight on these eigenvectors that are poorly sampled. And then this is the magic. This is what all the random matrix theory told us, right? There's something very funny happens if I increase the number of parameters. Actually, what happens is the gap opens back up. But of course, now I have more parameters than features, so I have to have a bunch of zero eigenvalues. So I have unsampled features, but the features that are sampled well. So it's super easy to tell the difference between well-sampled features and not well-sampled features. And this is what interpolation is. So even if I put an infinitesimal amount of regularization, the model can tell what directions I should pay attention to. It's no longer confused. And that is basically what happens. That's basically all it is. And this is true for no matter how complicated the machine learning architecture is, and this was done with regression. I just want to point out, right? And so this is like, what the actual gaps look like. It's not really important. The spectrum does this, blah, blah, blah. Okay, so here's an example. Right? Here is, right? As I said, the interesting thing is that variance it goes down because it's easy to distinguish noise from unused directions. Do I want to tell you something else? Yeah, there's some other weird stuff that is kind of interesting, right? So here's an idiosyncratic thing for the experts, right? So what's interesting is that I can think about whether my model is biased or not, right? So there's a big deal in classical statistics about whether my true data distribution agrees with the model that I'm using to fit. And what's interesting in machine learning is that if I look at biased models, even without noise, I can actually get variance. So basically the idea is that because I have biased models, I have all these unused directions that I don't see stuff, I basically use those unused directions. They act as an effective noise on my signal. So there's lots of little subtle things. It's not for this colloquium, so I'm gonna skip all those and just summarize my lessons, right? So there's 4 major lessons from our analysis. The first is that there's 2 sources of bias, model and data mismatch, but also unsampled directions in feature space, right? And this is what you're seeing. The reason you can't generalize to new groups is that you're biased. You're just basically doing random stuff in the directions you're not sampling. Variance comes from poorly sampled directions in the feature space. Variance but not bias diverges at the interpolation threshold, and interpolation is not overfitting. You can use as many parameters when we can easily tell noise from unsampled directions. So that's the key to this whole thing. Sure, go ahead.
And now your model doesn't become overfit.
In principle, if your thing is expressive enough, that's basically what the lesson is.
Yeah.
So you play computational cost. It's the usual thing. You pay computational cost, you can do it. But of course, you know, the point is that here, the way there's overfitting used in 2 senses colloquially, and what I wanted to distinguish is this one. This is overfitting to data drawn from the same distribution I care about. But when I go to these talks, everyone promises me I'm going to train on one data distribution and I'm going to somehow do awesome on another data distribution, you know? And that's a little different. That's a little different thing.
Okay.
I basically believe that can't happen because you're interpolating, right? So if you take the interpolation seriously, then the best you can do is hope that you have a few scattered data points here, and you're interpolating the few scattered data points that are similar enough to your out of sample distribution. You hope there's enough of that your interpolations are good. So the real lesson is that the way you should set up machine learning is you do stuff, you see where your model's bad, you go take more data there. That is how that's all it is. That's what people do. So that's all I wanted to say, I guess. Let me acknowledge some people and be done. All right, this was my random speculation about how I think overparameterization is generic in all complex systems, and we should start taking it more seriously. Because I think implicitly this von Neumann thing and the physics training is wrong for understanding complex systems. Like, I actually think it's really great. Like, when you make materials, everyone wants to synthesize them from scratch. I kind of feel like you should just throw lots of random crap in. No, I really think that's the lesson. I think the lesson is you throw lots of random stuff in, you have enough degrees of freedom, and it's actually overparameterized that you can fit stuff. So I actually think if there's a lesson for complex materials, it's that we should stop trying to design stuff. We should randomly assemble stuff, do DFT on it. I tried to convince Craig of this once. He laughed at me. And then do that. I think that's the future. I think actually, if you want to do machine learning, you randomly assemble, because I think it's all about over-parameterize. Anyway, so this work was done by Jason, who's actually at now a startup doing quantum chemistry stuff. It's over there. It's called Dayhoff Labs. They have a lot of money. They're in the startup structure. He's probably he's really having a good time. Someone actually I should tell you guys to get in touch with. They have this amazing PNAS where they find all this kind of enzyme catalysis stuff recently. And I tried to keep him in academia, but he refused to apply for jobs. Apparently startups, all my postdocs leave. And these people gave me money. Thank you so much.
Are there any other questions? Maybe one? Okay, no, we have to go to coffee break. Let's thank Professor Mehta again. Huh? People can ask their questions during coffee break. Let's thank Dr. Mehta again for his time. No, well, we were late.
Okay.
That was not your fault.